In this video, we'll be going over the hydrohalogenation of alkenes. We'll be going over the mechanism, the hydride shift, methyl shift, including Markonikov addition, and chirality. We'll be going over 6 practice problems and 2 synthesis problems. The first step in the mechanism is we draw an arrow from the pi bond to the hydrogen, and since hydrogen can only have one bond, the bond between the H and X has to break. The electrons in that bond attach to the halide. And the first step happens because the hydrogen is partially positive, and that's because the halide is electronegative, making it partially negative. It pulls the electrons in the sigma bond toward the X away from the hydrogen. That causes the nucleophile, the pi bond, to be attracted to the partially positive hydrogen. As a result of the first step, we can have 2 possible products. We can either have the hydrogen attached to the secondary carbon and have a positive charge on tertiary carbon, or we can have the hydrogen attached to the tertiary carbon and have a positive charge on the secondary carbon. Which one is going to be the major product and which one is going to be the minor product? Because a tertiary carbocation is more stable than the secondary version, which is more stable than the primary version of a carbocation, our major product is going to be the one with the tertiary carbocation. So now we're left with a tertiary carbocation and a negatively charged halogen. The negatively charged halide is going to attach to the positively charged carbocation, giving us our major product, 2-methyl, 2-bromo-butane. The carbon where the halide is attached to has 2 of the same groups. It has a methyl group here and a methyl group here, making it achiral, so it only has one answer. Now let's go over the next 2 problems that include a hydride shift and a methyl shift. As always, we draw an arrow from the pi bond to the hydrogen, and the bond between the H and the halide breaks. Now our question is, which one is more stable? Would the secondary carbocation be more stable or the primary? And the answer would be the secondary. So we're going to attach our hydrogen to the primary carbon. So we'll have this new bond. And we'll have a positive charge on the secondary carbon here. Before we attach the halide, we have to do a hydride shift. A hydride shift occurs when there's a secondary carbocation or primary carbocation next to a tertiary carbocation. The green bond and the H will reattach to the secondary carbocation in this situation. And the driving force for this is stability. A tertiary carbocation is more stable than a secondary carbocation. That's why a hydride shift occurs in this situation. And now we can finally attach our iodide to the positively charged carbocation, giving us 2-iodide, 2-methyl butane. Now let's go over the last problem that includes a methyl shift, and I'm going to change this group into a CH2CH3 group to introduce stereochemistry. Like always, the first step is we draw an arrow from the pi bond to the hydrogen, and the bond between the H and the halide breaks onto the Cl. Another way we can determine where to add our hydrogen is by choosing the carbon with the most hydrogens. This primary carbon has 2 hydrogens, and this one only has 1 hydrogen connected to it. Because the primary carbon has 2 hydrogen, we're going to add the 3rd hydrogen to it. And we're left with this here. When we added our hydrogen to the carbon with the most hydrogens, that is known as a Markonikov addition. We've done it in the past 2 problems, we just haven't mentioned the name of it. So this is another method of where to add the hydrogen instead of using stability like we did in the first 2 problems. And before we can add our chloride ion to the carbocation, we have to do a methyl shift. A methyl shift occurs when we have a secondary carbocation or primary next to a quaternary carbon. The quaternary carbon has 2 methyl groups. I'll show them in green, and we have an option to choose. I'm going to move the one on the top here, and we're going to move it to the positive charge. Moving the methyl group, known as the methyl shift, we get the methyl group on the positive charge where it was, and the positive charge moves to where the methyl group was attached to. And now we can attach our chloride to the positive charged carbon. And this time we can get 2 major products. This time we can get a wedged chlorine or dashed chlorine. And the reason for two answers is because of chirality. If we focus on the carbon where the chlorine is attached, we have four different groups, making the carbon chiral. There's a chlorine, a methyl, and an ethyl group, and an isopropyl group. Because we have four different groups, we can have a wedged chlorine or a dashed chlorine. Now let's look at the chirality of the carbon above. It has a halide, an ethyl group ET, and two methyl groups. Because we have two of the same groups on the same carbon, we cannot have a wedge or a dash. Okay, so go ahead and try these next three problems on your own. Try finding the major products of each of one of them, and try doing the mechanism if you'd like. For the first one, we have a pi bond on a primary carbon and a secondary carbon. And we know secondary carbocation is more stable than the primary carbocation, so we know our positive charge will form there. And that's where our chlorine will attach to, and we'll have our hydrogen attaching there. And we will have two answers for our first problem because it is a chiral center, so we'll have a chlorine on a wedge and on a dash. The four groups of the carbon are different. We have an ethyl group, we have a methyl group, we have a hidden hydrogen, and our chlorine. Four different groups making it chiral, so we do have stereoisomers. For the second problem, I'll do the mechanism really fast. We have a pi bond going to the hydrogen, and the bond between the H and bromine breaks. Using Markonikov addition, we know to add the hydrogen to the primary carbon, because this one has 3 hydrogens compared to the 2 hydrogens on the other secondary carbon. We'll have a positive charge on the secondary carbon. And before we can add our bromine to the carbocation, we do have a hydride shift, because we have a tertiary carbon next to a secondary carbon. We're going to move from the green bond to the positive charge of the secondary carbocation. Because of the hydride shift, our carbocation is now formed on the tertiary carbon. And this one also has two answers because we have a chiral center. The bromine will be on a wedge and on a dash. The tertiary carbon is chiral, and we can look at it through a line of symmetry. The group on the left is not the same as the group on the right. It's missing the methyl group. If the left side did have a methyl group like the right, it would mean it would be achiral. It would be achiral, so it would only have one answer, no wedge or dash. For the third problem, we have a pi bond on a secondary carbon and on another secondary carbon. Therefore, our iodide can attach equally to either carbon. For the first answer, we can put our iodide down the middle. We can't have a wedge or a dash because it is not chiral. It is achiral, and that's because we have two of the same groups, which are two ethyl groups. And I'll show where we put the hydrogen. We can get the other two answers by putting the iodide on the other carbon. We can put it on a wedge and one on the dash. And that is because the carbon is chiral. Now go ahead and try these final three problems on your own and see what you come up with, and then we'll go over it. For the first one, we have a pi bond on a primary carbon and a secondary carbon, and that's next to a quaternary carbon. So we know when the secondary carbon gets a positive charge, the methyl is going to shift. The carbocation will move from the secondary carbon to where the quaternary carbon was. We'll have a wedged bromine and a dashed bromine as well, because it is a chiral center. The second one is tricky because we have hydrobromic acid and a peroxide, and all that means is an anti-Markonikov addition. So we'll put our hydrogen on the carbon with the least amount of hydrogens, and our positive charge will go on the other carbon, where our bromine will attach. And this is our final answer. Now let's go over the tricky third one. If we place a hydrogen on the tertiary carbon, we get a primary carbocation. If we place it on the primary carbon, we get a tertiary carbocation. Normally the tertiary carbocation is more stable, but in this case the primary is more stable because of resonance with the methoxy group. To show the second resonance structure, we'll use an electron pair to create a double bond. When we're able to share the positive charge with another part of the molecule, like in this case, oxygen, that is more stable because we are sharing the positive charge with the two. It's kind of like carrying the weight with one hand and carrying it with two hands. It's a lot easier with two. So it's better to have a delocalized positive charge, making it more stable. So that is why we're going with a primary carbocation rather than a tertiary, and that's where we'll attach our chlorine. And it is a chiral carbon, so we'll get a wedged chlorine and a dashed chlorine for our answer. Now let's do some synthesis. What best alkene can be used to synthesize 3-chlorohexane? If we count the carbons in the product, we have 6 total carbons. So our starting molecule will have 6 carbons. In reverse order, to have the chlorine attached to the third carbon, we had to have a positive charge. To get a positive charge on the third carbon, we had to have a hydrogen placed on that carbon or on this carbon, which means we can either have 2-hexene or 3-hexene. Which one is correct? It turns out that 3-hexene is the correct one because we can attach our chlorine to either carbon and we'd still get 3-chlorohexane. If we chose 2-hexene, we'd also get 3-chlorohexane, but we also get a mixture of products of 2-chlorohexane. Now let's quickly try one more. If we have our bromine attached to that tertiary carbon, that means we have our positive charge on that carbon. And we don't want to put our double bond between the two tertiary carbons because we'll get a mixture of products. We'll get a bromine there, which we do not want. So instead, we'll put our double bond on either methyl, on this one or the other one, and it'll give us the same product. So that is our final answer. If you have any more questions, please leave a comment so I can try answering. I'd be happy to do so. And please consider liking and subscribing for more future content if this video helped. It keeps me motivated to create more videos like this. So thank you and have a good day.